Hi everyone. Today's lecture is going to be on the addition rule. We're still doing probability. And we have a Venn diagram. That's what these are. There's a little history there that you're welcome to read. But we're going to do a little bit of practice so we can kind of get an idea of what it is that we're talking about. So we have a survey of a local school asked students what club or clubs they were affiliated with last year. And the Venn diagram finishes the results here. Now if you look here, all of them that are in this circle are the students that were in the drama club. All of them that are in this circle are in the music club. The ones that are on the outside completely are ones that are not in the drama club nor in the music club. So my total sample space is going to be 9 plus 15 plus 7 plus 12, which gives me 43. So 43 students total are part of this survey. Now this is the number of students that are in drama. Now when we do the number of drama, again that's everybody in this circle, so that's going to be 9 plus 15. So there are 24 of the surveyed students that were in the drama class. Now the music class, again, is everybody in this here. That's going to be the 15 plus 7, giving us a total of 22 students that were in the music club. Now here's our and our or situation. So the number of members that are in both in the music club and the drama club, meaning they are in both clubs at the same time, that's going to be right at this intersection here. That's going to be a total of 15. And the number of people that are in the music club or in the drama club, meaning they only have to be in one of these two, is going to be this number here. It's going to be the 9 plus the 15 plus the 7, which gives us a total of 31. Now you'll notice we have overlap on this one, and you'll notice when we counted the number of people in the drama club, we included the 15, and in the music club, we included the 15. So we're actually double counting there if we count it all the way across. This is why when we did the or, we did the 9 plus the 15 plus the 7. Let's move on to disjoint, or mutually exclusive. What this means is that there is no member of one group that is also a member of the other group. So what we get here is that the probability of event E or of event F happening when they're disjoint like this is going to be the probability of event E plus the probability of event F. And here's a nice picture where you can actually see that there's no connection between the two. And we'll do a little practice. So we have a support group that consists of preteens, teenagers, and adults. We're going to pretend for right now that teenagers are not adults, even though in real life we know that they are. And what we're going to do is we want to know what is the probability that they are a preteen or an adult if we randomly select one of them. Well, let's figure out the sample size first. That's going to be the 10 plus the 23 plus the 12, which in this case is 45. So what's the probability? And again, you can see that they're disjoint. So the probability of them being a preteen is 10 out of the 45. And you can reduce that. You can turn that into a decimal. It's all good. So we could say 2/9. And the probability that they are an adult, there are 12 adults, so that's 12 over 45. And that's going to give us, let's see, we can reduce 3 out of that. That's going to be 4 over 15. Now, the probability preteen or an adult is just going to be the sum of the two, because they are disjoint or mutually exclusive. That gives us 22 out of 45. That is when we are disjoint. When they're not, then we run into a rule called the general addition rule. This says that if we want to know the probability of E or F, that's going to be the probability of E plus the probability of F. But if you remember, when we're here, if I did the probability of drama plus the probability of music, I counted that intersection 2 times. So the rule says we got to subtract off one of those. And this is going to be the main theme for us from now on, for the rest of this lecture. Now, some of you may or may not be familiar with playing cards. There are 52 cards in a standard deck. The cards are broken up into what are called 4 suits. We have clubs, diamonds, hearts, and spades. 2 of those are red cards, and 2 of those are black cards. So the red cards are here. The black cards are here and here. Now, it goes 1 through 10, and the ones we call aces. And then after 10, we have 3 what are called face cards, Jack, Queen, and King, giving us a total of 12 face cards. So we're going to start out by finding the probability of each of these. And the directions here say as a simplified fraction, that's fine. The probability of drawing a king, well, the denominator is going to be 52 for sure. How many kings are there? Well, we can come back, and we can see that there are 1, 2, 3, 4 kings. Meaning there's a 1 in 13 chance that you would draw a king if you randomly drew a card from a standard deck of cards. The probability of drawing a jack. How many jacks are there? Well, just like kings, there are 1, 2, 3, 4 jacks out of the 52, which reduces to 1 over 13. Once again, this means that there's a 1 in 13 probability of randomly selecting a card from a standard deck of cards and getting a jack. Now, because kings are not jacks, they are mutually exclusive. So when it says draw a king or a jack, probability of A or B, well, we're just going to add those together. 1 over 13 plus 1 over 13 gives us 2 over 13. So these are mutually exclusive, so these are disjoint. This next part, they will not be. What's the probability of drawing a red card? Well, how many red cards are there? Once again, there are 13 in each deck, 1 through 10, and then 3 more. And their 2 suits are red. That gives a total of 26 out of 52 cards are going to be red, or exactly 1/2. The probability of drawing an ace, well, let's go back. How many aces do we have? 1, 2, 3, 4 of them. Now, what's the probability of drawing a red card or an ace? Well, we have to keep in mind that there are red aces. So the probability of drawing a red card or an ace is going to be the probability of drawing a red card plus the probability of drawing an ace minus the probability of red aces. Well, we know the probability of red. We got that up here. I'm going to keep it in its denominator 52. Plus the probability of it being an ace. Here we are. That should be B. Is 2 over 52. But how many red aces are there? Well, we saw there are 2 red aces. There's the ace of diamonds and the ace of hearts. So we counted those twice. And what I mean by that is we counted them with the aces and we counted them with the red cards. So this should be a 4. Minus 2 out of 52. Which gives us a total of 28 over 52. Which reduces to 7 over 13. So what's the probability of drawing a red card or an ace? It's going to be 7 out of 13. So you can see we have to subtract off that overlap. Yeah, so that overlap here is going to be the 2. All right, moving on. All right, so here we have a 12-sided die is rolled, resulting in a sample space of 1 through 12, meaning the only possible answers that we can get when we roll one 12-sided dice is 1 through 12. And we have a couple of subsets. Set F is going to be this set here, and set G is going to be here. And are they mutually exclusive? Meaning, are there any numbers that are in both at the same time? And the answer to this is that they are not mutually exclusive, because they share a 10 and they share an 8. So list the outcomes for events F and G. Well, the keyword here is and. That's going to be 8 and 10 because of the and. So now we're going to list the outcomes for events F or G. Well, that's going to be all of these. So that's going to be 2, 4, 6, 8, 9, 10, 11, and 12. And you'll see that there are a total of 2 here. And there are 1, 2, 3, 4, 5, 6, 7, 8 here. So what's the probability of F? Well, we know the denominator will be 12. And how many are in F? We have 1, 2, 3, 4, 5 potentials in F. Probability of G? Well, we have 1, 2, 3, 4, 5 out of 12 here. And that brings us to find P of F or G. And all we're going to do is just count what we have here. So the number of F or in G, we have a total of 8, as you can see here, out of 12. I know that some of these can reduce, certainly that one can. Now we're going to use the addition rule. So to find the probability of F or G, we're going to have the probability of F plus the probability of G minus the probability of F and G. So we'll take the probability of F, which we have over here, 5 over 12, plus the probability of G, which we have here, which is 5 over 12, minus the probability of the AND case. There are 2 of those, 2 over 12, because we counted 8 and 10 2 times in here. So that's going to give us a total of 8 over 12, which you can see is the same as counting them. Works out pretty well. Here we have number 4. And we have a university with a total of 371 undergraduate students. And it's broken down by class, and we're given the totals. And are they satisfied with the student government or not? So we'll start here. What is the probability that he or she is satisfied with the student government? Well, my denominator for sure is going to be 371. And so how many of them are satisfied with the student government? That'll be the 236. Next up, what is the probability that he or she is a junior? Well, probability of being a junior is going to be, again, over 371. How many of them are juniors? Here we have the juniors, and we got the total down here. It's an 89. What is the probability that he or she is a junior and satisfied with the student government? Well, we're going to go to the juniors, and how many of them were satisfied with the student government? That's going to be the 65. Next up, find the probability that he or she is satisfied or a junior using the general addition rule. So we want to know the probability of being satisfied or a junior. Well, that's going to be the probability of being satisfied with the student government plus the probability of being a junior minus the probability of junior or student. Well, that's going to be 236 over 371 plus 89 over 371 minus 65 over 371, which gives us a total. You can certainly use your calculator, 260 out of 371. And for the last part here, find the probability that it's a not satisfied and a freshman. Well, again, we're going to go to the table. Here's not satisfied, and here's freshman, so that's going to be a total of 15 out of 371. Next up. So you can see the theme here. So the probability of A or B, given these probabilities here, well, this is going to be, again, the probability of A plus the probability of B minus the probability of A and B. That's the 0.35 plus 0.45 minus 0.15, which gives us a total of 0.65. And if we want to fill in this Venn diagram, that goes in the middle, but we got to get a little creative here. So what I'm going to have to do is notice that all of A should equal 0.35, including the 0.15. So 0.35 minus 0.15. That's going to go there. Same with B. 0.45 should include the 0.15. So what's left over here? Well, that's going to be 0.45 minus 0.15 and 0.3. Next up. Now we're looking for P of B. So now we're going to be using this same formula up here. I'm going to cut it off. This same formula here. But now this is our unknown, and we're given these three pieces. So it's going to look like this. P of A or B once again is P of A plus P of B minus P of A and B. So this they gave to us. right there, right here. 0.65 equals P of A, which is here, 0.6 plus P of B, this is our unknown now, minus P of A and B. I'm going to combine out my like terms here. And this goes back to old-fashioned algebra. Oh, that's a plus. So I'm going to subtract 0.5. Which means P of B will be 0.15. All right, so here we have data. We have total number of births of ages from 15 to 54. I want to point something out here. Can you see that the majority of multiple births are from the age group of about 25 to 39? That's capturing the vast majority of these women. So first off, I need a total. And actually, I'm going to move on from here. I know that that's not in the notes, but this has taken quite a while. I want to thank you, and there will be more videos to come.